Hello, everybody. Welcome to the session. Welcome to this series, solution series. We are going to help you in this particular summary series for your board examination so that you can excel in that and you can score the best. So today is the first topic is solution and colligative property. This chapter is of extreme importance. Wherever you go in physical chemistry, you will see that this chapter has some linkages with it, right? Solution chapter has the very first topic to be understood is concentration terms. And when we start discussing science, when we just move to non-medical, as we say, science subject in 11th grade, just after your 10th, the first topic that we study is mole concept, or we say that as an some basic concept of chemistry. Those some basic concept of chemistry ends with concentration terms, for example, molarity, molality, right, everybody? And this comes the chapter solution and colligative property having the first topic concentration terms. So you can see that how 11th and 12th they both are connected to each other. So without any delay, everybody, let's start our session and let me quickly introduce myself. My name is Dr. 𝐒𝐿𝐉𝐿𝐿𝐿. I study from IIT Delhi and I did my PhD in chemistry from Indian Institute of Science. I believe you people know what is that institute. So I did my PhD in chemistry from IISc Bangalore, right? And since after that I have been teaching professionally, so it has been already many years. I can say that. So to count, there are several other experiences that I hold. For example, I taught chemical engineering in IIT Guwahati, in the year 2020, right, everybody? After that, I have been professionally teaching students for JEE examination and for NEET examination. So I am here to make you people doctors and engineers. The students who are sitting at home will be having various aims in their head. For example, they would like to be a good doctor in future, or maybe an engineer, or some would like to be an architecture, or many other visions would be there in your mind. So I'm here to help you with that. So I myself have studied from IIT Delhi, as I was telling you, and then I did my PhD in chemistry from Indian Institute of Science of Bangalore. Post that I taught chemical engineering first year students in IIT Guwahati. Right, everybody? Let's start with our next topic for today. All right. So this is the content. This is how we are going to take our session. First of all, we'll discuss concentration terms. Then we'll move on to something called solubility. Then we'll discuss colligative property, and we will conclude our session by discussing something called very important Wendt Hoff factor. This is the heart and soul of this chapter. So please be connected with me and watch this session up to the end so that you are totally benefited with what exactly this solution chapter is all about. Okay, so let's begin, everybody, with the first topic. What are concentration terms? Be very focused. So percentage concentration terms are the first thing we are now going to discuss at first. Okay. Now, there is something symbol written as a percentage. Whenever we talk about percentage is always out of 100, right? And this W is the symbol used for mass. This W is also a symbol used for mass. So what I mean by writing this W by W is weight by weight percentage, or you can call it as percentage weight by weight. Very important term it is. So suppose I say that I have 20 percentage, anything, maybe 20 percentage methane, or instead of that, let's say I have 20 percentage of some solid we can take. Maybe we can take what solid you want to take. Let's take urea. Okay, 20 percentage urea, and that is weight by weight. What does this mean? In this entire chapter, we need to understand what are these terms mean. So they will ask you question by giving this statement. 20 percentage means 20 gram of urea in 100 gram of solution. This is very important to note that It is out of 100 gram of solution. Perfect. Great. So its weight in, I have written down the definition also for you. You just need to download these notes. It will be just full proof for you. Ready-made notes for you. You need not to do another practice of making the notes. And I will tell you all the books that are required, all the things that are required to excel best in your board examination, right? So it's a weight in grams. Be very careful. The units are grams of the solute. So there are two components in solution chapter we study. In a solution, there will be two things. One is called solute. The other one is called a solvent. Solute is generally represented by 2. What is 2? 2. A numeric. And solvent is generally represented by, generally, it's not a hard and fast rule. Solvent is represented by 1. Or in some standard books, you would see that solvent is also represented by A, symbol A, or solute is represented by symbol B or the letter B. Understood? So in this chapter, somewhere here and there, you might see that 1 or 2 terminology or A or B terminology is used. So you need not to be confused. This is of the solute. So I can say that the weight of the 2 divide by total weight. Remember, total weight of the solution. Total weight would be W1 plus W2. Can I say that, sir, it looks like how much fraction of it you have? Right. This seems to be the fraction. If I multiply it with 100, this will become percentage weight, by weight. When you have both the things in gram and gram, the units of numerator and denominator both are gram and gram. What is the unit of this? What is the unit of this quantity, everybody? Can you please tell me? What is this unit? There will be absolutely no unit, because numerator and denominator both are having gram and gram. They cancel each other. Right. Now let's move to the next, a sister concentration term of weight by weight, which is weight by volume. So we can say something 20% weight by volume of, let's take another solution, urea. Weight by weight. So this time I had 20% weight added to some other solute or other solvent. Solvent, remember, solvent need not to be liquid always. I am going to show you many examples where solvent can be anything, solute can be anything, can be solid, liquid, gas, can be anything. So you just have to take out this thing from your head out, that this solvent, the solvent always have to be liquid. No, they can be liquid, they can be gas, they can be solids also. So this time we have 20% weight by volume of urea. Then I will mean that there are 20 gram of urea is present in how much? 100 ml. 100 ml of the solution. Remember, 100 ml of solution it is. Understood? Very good. So weight in grams of the solute. Solute is something which is present in less amount per 100 ml of the solution. Remember, if no information about solution is given to you, how much of it is there, and if the solution says it is 120 gram, you have to take 120 in the denominator. If it says no information of solution is given to you, then you have to very easily go with 100, right? Okay, obviously you have to multiply it with 100 to get the percentage. If you keep it the ratio ways, that becomes the fraction. Okay, finally we have volume by volume. Now we can take 20% ammonia dissolved in water. Now this is going to be, or instead of like taking ammonia, let's take Br2. You are going to study Br2 in water, which is one of the beautiful reagent in organic chemistry used to test the unsaturation of the molecule. So 20% Br2 in water, bromine water, red color, it's red color solution. Volume by volume. So this is taken in ml, this also taken in ml. So how much of it is volume in ml of the solute per 100 ml of the solution? Are all these three clear, everybody? Is that clear, everybody? Please tell me. Tell me in the chat box, is it clear? Weight by weight, weight by volume, volume by volume. These are the three major things we need to understand, right? Okay, these were the very simple one. Let's move ahead to the next one. Now we have very important something called molarity, and molarity is represented by a capital symbol, capital M, capital M. Now what does it mean? Molarity is represented by capital M, which means it is equals to the number of moles of solute. मैंने solute को B बोला, solute is B here, right? So number of moles of solute present in the total volume of solution, but that volume of the solution has to be in liter. Make sense? Okay, I can expand this to weight of the solute divided by molar mass, mm, molar mass of that solute. This makes the number of moles of solute multiplied with volume. But remember, volume has to be in liter. Suppose you do not have that in liter, what to do? Convert that. As simple as that, convert it. So it will become weight of solute divided by molar mass of solute into volume in ml, and then 1000 on the top. So this becomes your molarity. Can you please quickly tell me what will be the unit of molarity? And trust me guys, in my so many years of experience of teaching, I have seen that people are so afraid of these concentration terms, but they are not hard. You just need to sit down with patience and calmness and think what these statement actually means. You just have to find out what is missing in the question and then hunt for it. I'll tell you all the ways also to solve the question so that you make 100% rightness there. Okay, so what is the unit, everybody? Gram per mole. Okay, so the unit will be mole per liter. Gram divide by, let's divide it by gram per mole into liter. Correct, everybody? Right? That's the thing. So gram cancel and it turns out to be mole per liter. That becomes the final unit. In this chapter, you need to be very careful about the units. I'm repeating, and I can repeat this 1000 times. It has to be you have to be very careful. The next one, although it's not a part of your syllabus, I mean, it is not discussed in NCERT, but I didn't want to miss it. Hence, I have brought it here. If you want, you can learn it. So learning is never bad, right? Okay, so normality is represented by a capital letter N, which means it's equals to number of equivalents divided by total volume of solution in liter. Exactly the same, similar definition, but instead of number of moles of solute, we have number of equivalents of solute. Now we need to understand number of equivalents, how to calculate that. Number of equivalents would be equals to the given weight of the sample, given weight of the solute divided by its equivalent mass. I will not go into the detail of it because this will come again in something called electrochemistry, because there we have to follow something called Faraday's law. There also we require equivalent mass. Also it is used in redox chemistry chapter. Now equivalent mass is something which is equals to molar mass divided by N factor. This is my favorite, personal favorite, very nice exercise to calculate things, N factor. Okay, what is N factor? That part we will deal in some other like redox or electrochemistry chapter. As of now, you should know the formula, as since it is not discussed in NCERT, so chances are very thin, maybe 0.0001% that the board people would ask this question in your examination. Anyways, we are here to learn things, right? First, our aim, our focus is for board examination. Now the third comes as a mole fraction. You know fraction? Fraction is something out of the whole. Something out of the whole. So if I say I have two components present, A and B, we are discussing a binary mixture. Binary means two. Binary mixture. I want to calculate mole fraction of one. So mole fraction is represented by a symbol called chi. Suppose I want to calculate mole fraction of solvent, that should be equals to its own number of moles divided by total number of moles. So these things are so easy, we know them. Yes, I know. But how to use that in formula? You know, just after the session ends, I expect you people to solve all the previous year questions that you might have with you, which have been asked in the board examination. That thing also you should do. Plus, you should practice something called NCERT at fingertips. You should practice this book on daily basis. NCERT at fingertips. It's available on Google. If not, then you can ping me. I can share with you guys, right? So NCERT at fingertips should be on the regular basis. You should be practicing. Plus our material, a study material. Now the ratio of the number of moles. This is the ratio. So before I finish talking about mole fraction, everybody write down in the comment box what is the mole fraction ka unit. What is the unit of mole fraction? Similarly, I can write 𝐶𝐈 should be equals to number of moles of B divided by total number of moles, and what are they? Total number of moles are Na plus Na plus Nb, Na plus Nb. Now I want you people to also tell me what is the summation of these two mole fractions. 1. Absolutely it is 1. Why? Because denominator is the same. I can take an LCM. Numerator also comes out to be the same. So one thing is very clear. If you are provided with 𝐶𝐈, do you need to separately do the calculation for 𝐶𝐈? No, just subtract it from 1. You will get 𝐶𝐈 in hand. Understood? Alright. Now, these were the thing. So you people are telling me the unit of this mole fraction. Yes, it's a unitless quantity. Remember, it's a unitless quantity. Since it's a fraction, whenever you see, not just this, whenever you see that there is a fraction, the ratio taken, and both the numerator and the denominator are of the same unit, overall there will be no unit left. It will be unitless. All right, everybody, these three are extremely important. I am sure there is no doubt so far. Let's move to the next topic, what is called as a strength. What is strength, everybody? Strength is how much of the solute in grams you have, how much of the solute in grams you have in 1 liter of the solution. Generally 1 liter of the solution. If the solution ka unit, how much volume is present to you, that is given to you, then you have to take that number. So strength is equals to the weight of the solute, and that has to be in gram. Very, very, very important. And then volume has to be in liter. Whose volume? It is solution. Solution ka volume. Are you with me? Are you people following? Right? Okay. So unit goes like gram per liter. Gram per liter. Very important unit. Then we have molality. It's a cousin. Again, a cousin concentration term of molarity. Little different. Represented with a small symbol, small letter m. And that's equals to how many number of moles of solute is present in 1 kg of 1 kg of solvent. 1 kg, or let's take weight of solvent. I'm repeating, it's solvent, not solution, and that weight has to be taken in kg. So what would be the unit? Let us expand this formula a bit so that we understand what are present inside. So weight of the solute B divided by its molar mass. Then we have weight of solvent, and I was saying solvent is used as, solvent symbol is A. So can I use A here? Right, everybody, let's say W of A but kg. Understood? Okay. Now what will be the unit of molality? Molality is also represented as molal. Molarity is also represented as molar. You might be saying, sir, you are emphasizing a lot on molar, hai na? So molar and molal, they sound same. So to make a clear distinction between what is molar and molal, we have to stretch the word a bit. Molar. Now this is equals to the number of moles per kg. Is that clear, everybody? Moles per kg. And for molarity, it was mole per liter. Okay, now let's move to something called ppm. Very useful for calculating hardness of water, very useful for calculating the amount of pollutants present in our atmosphere, all those things which are basically present in very less quantity, very less quantity compared to the huge amount of the solvent or the solution. So ppm is equals to, we can calculate it three ways or many ways rather. We can say that the weight of solute present in the total weight of the solution. Total weight of the solution. I'm writing it as solution. Total weight of the solution. Alright. Multiply it with 10 raised to the power 6. This has to be in gram. This also has to be in gram. Understood? Weight of the solute present. For example, there is a water sample which is contaminated with mercury. So I'll take how much gram, how many grams of mercury is present in water. Divide by total weight of the sample. But remember, both the units should be in gram and then multiplied with 10 raised to the power 6. 10 raised to the power 6 takes care of the million factor. And a ppm, parts per million. Parts out of million. In 1 million, how many parts of solute are actually present? You can calculate it with volume wise also. So volume of solute divided by total volume of the solution. Total volume of solution. Multiply 10 raised to the power 6. Again, this becomes ppm in volume range, in volume terms. Remember, very important, 1 ppm. Generally in examination, they write that 1 ppm is equals to how much, or prove it. 1 ppm is equals to 1 mg in 1 kg or liter. Let's take, we are taking a water sample, simple water. So 1 mg in 1 kg. Let's prove that how 1 ppm is equals to this much amount. So according to this definition, let's first say that 1 mg of solute is present, and in terms of grams, how many they are? 10 raised to the power minus 3 grams. Perfect. And kg is the solution ka total weight. How much is this going to be in terms of grams? It will be 10 raised to the power 3 grams. As I said, this has to be mandatorily in gram and gram. Okay, I remember this question has been asked many times. So just simple question. Multiplied with 10 raised to the power 6. Do you see that? Everything is settled around each other, and this comes out to be equals to 1. So 1, it is what? It's ppm, 1 ppm. Understood, everybody? So 1 ppm is equals to 1 ppm is equals to 1 mg per kg. Or we can say 1 ppm is also equals to 1 microgram present in 1 gram. Microgram in gram. It need not to be 1. Let's delete 1. It has to be simply what? Gram. It's equals to microgram per gram. Are you guys following? Mg per kg or microgram per gram. Understood? Let's move ahead. All right, everybody. Now we have ppm, weight by weight. As I have already explained to you, I have brought to you the formulas. You can just download the PPT and it will be your notes ready. So weight in grams, extremely careful. Be very careful about it. 10 to 10 to the power 6. In terms of volume, you can use this formula. And when both of them are volume, that also can be used. Now we have ppm, moles per moles. That's also possible. Number of moles of solute divided by number of moles of solution. When do we use some of a ppm type of calculation? When the number of moles of solute are too low compared to the total number of moles of solution. That makes it equals to ppm in a very low range. For example, hardness of water, also for all pollutants quantities. Now I have brought to you the very important table, which is about temperature and in temperature dependency and independency of these concentration terms. Expect one question from here, and remember, from this chapter, one question is 100% sure, pakka, 100%. There's something called strength, everybody. We molarity, normality, percentage weight by volume, percentage volume by volume. They all have volume factor associated with them. And wherever you have volume, they all will be temperature dependent. And my question to you guys, you will be answering in the comment box, what happens to molarity when you heat? When you increase the temperature, what happens to molarity? And then we have temperature independent. These are volume independent. There are no volume factor associated with them. Hence, they all are temperature independent. Parts per million, parts per billion also, that would be out of 10 raised to the power 9. ppm was out of 10 raised to the power 6. Percentage weight by weight also does not have any volume factor associated with it. Hence, this also becomes a temperature independent. This is very favorite question of board examiners, specifically for CBSE. They ask that which property do you think is temperature dependent and why? In other ways, they ask the question that what happens to molarity when you change the temperature? The two cases, increase temperature and then decrease the temperature. I want all of you to answer in the comment box. Let's start our next topic for today, which are the types of solution we are now going to study. Okay, the types of solutions, now we can categorize them on the basis of two things. One is based on the number of components, how many components are present. Either they can be two or there can be many also. So tertiary, quaternary, all those are possible. But we are going to stick to just binary solution. Another binary solution, we may have homogeneous or we may have heterogeneous solution. But we will be keeping our eye on both kind of solutions, homogeneous as well as heterogeneous. We'll see that in a while, how to do that. This we are not going to study at all. Let's discuss the categorization of the solutions on the basis of the type of or the phase of components. Suppose we have to make a gaseous solution. How do we actually name that solution overall on the basis of what is the phase, overall phase? So the thing which is a mixture, basically it looks just a gas, like air around us, like just air. And do you think the air around us is just oxygen? No, it's a mixture of many gases. Then, for example, gas into gas, one question you can expect this from this table. I'm telling you, gas and gas, mixture of O2 and N2 gases together makes overall a solution which just looks like a gas. Then we have liquid and gas ka mixture. For example, chloroform. Chloroform is a liquid. I can mix it in a nitrogen gas. How, sir? So the chloroform actually has a volatility nature. It's volatile. It evaporates on its own and then gets mixed with the nitrogen gas, right? Solid and gas. So the camphor also has a property of something called sublimation. So you keep it at room temperature, it absorbs the energy from the environment, the climate around it. This is called thermal energy, and hence it starts subliming and then mix with the gas present around it and becomes, overall solution becomes like a gas. Are you understanding, guys? Overall it looks like gas. Hence I have said this is solvent. Here the gas is solvent, here the gas is solvent, here also the gas is solvent. So this question should not be there in your mind anymore. Can solvent be gas? Can solvent be solid? Yes, why not? और भी जवाब आएंगे. So solid solutions now we need to have solids as the solvent, something which is present in more amount, huge quantity. For example, gas. Now this becomes your very first topic of hydrocarbon chapter. How do we obtain alkanes from alkenes? That process is known as comment box. Write down in the comment box, what do you do to carbon-carbon double bond to make carbon single bond? Of course, there are other valencies satisfied by hydrogens or something else present around carbon. But what do you do? I want to add two hydrogens on carbon-carbon, across carbon-carbon double bond to get a saturated alkane. This is a saturated alkane, single chain, simple chain, aliphatic. That process you have to write down in the chat box and tell me. This reagent is actually used, hydrogen in palladium. So what we do, palladium is used in a powdered form or in a very small sized form. Nowadays we use nanotechnology. So in a nano sized palladium, and then we use a balloon filled with hydrogen gas. Hydrogen goes, sits on the palladium surface, adsorption happens. Adsorption. Now hydrogen split, hydrogen molecule. I personally call hydrogen molecule as a queen of sigma bond because it's very, very stable sigma bond. This splits into, due to palladium, interaction happens, this splits into nascent hydrogen, and then it undergoes addition across carbon-carbon double bond. This process is known as, rightly pointed out, this is known as hydrogenation process. When you add hydrogen. So this solution actually looks like this is just a solid. Where is the gas? Nothing. There is no gas appearing present in the reaction vessel. It is just the palladium which has hydrogen gas adsorbed on it. Very good. Now we have solid solution. Solid solutions, again, we will be using liquid, solid, and amalgam of mercury is any metal that you take with mercury, it will mix up with it. Most of the metals, I'm not saying every metal in the periodic table mix up with mercury. Many metals, they do not form amalgam. For example, ruthenium doesn't do that, iridium doesn't do that, rhodium doesn't do that. So you should be extremely careful about it. So amalgam of the mercury with sodium, that makes a solid solution. So solid, liquid goes into solid. So what is a liquid? Mercury is liquid. You should know that at room temperature, which metal is mercury, which metal is liquid, mercury it is. And also you should know there is another metal which melts at room temperature. Write down in the comment box. You have to answer to me which metal melts at just room temperature. Room temperature, you can consider it to be 30 degrees. Although room temperature by definition is 25 degrees, but I am asking you to consider if RT is equals to 30 degrees, which metal melts at that temperature. Okay. Now we have copper dissolved in gold. For example, my ring has a, I will not tell you the composition of this, but copper dissolved in gold, something when the two metals are taken into together and overall it looks like solid, solid plus solid, overall solid. This is now liquid solutions. Soft drinks. How many of you like soft drink? I do like, but I avoid. So CO2 dissolved in water. Carbonated drinks. Pepsi, Cola. Liquid solution, liquid. Let's not talk about this. Ethanol dissolved in water. No. Don't do that. Solid and liquid. Glucose, this you can try for keeping yourself hydrated, keeping yourself up to date with energy. Glucose in water. I am sure this entire table is clear, everybody. If there is any doubt, you can reach out, you can discuss. Okay, now let's discuss something called solubility. There are three kind of solution we need to study. First of all, something called unsaturated, and the second one is called saturated, and the third one is super saturated solution. Now what is solubility? Solubility is the amount of the substance which can be the max amount of the solute that can be dissolved in a solvent. Max. This term you might have studied in ionic equilibria, I am sure. Solubility product ke chehre, solubility product. Correct? So solubility is something that's the max amount of a solute you can dissolve in a solvent, particular solvent. Now if you dissolve less of the substance than its solubility, then it becomes an unsaturated solution. If you are just matching with the solubility concentration, then it becomes a saturated. And if you are forcing it to dissolve more and more, it becomes a super saturated solution. Understood? Okay, now we need to see that what kind of solutions, what kind of factors that vary the solubility of one component into another component. For example, liquid in liquid, for example, gas in liquid, and also solid in liquid. What are those components which affect? What are those factors which affect? First factor is the nature of the solute and the solvent. What is the thing which wants to get dissolved in something? I have used thing and something. Now what are those? Solute and solvent. You might have heard about like dissolve like. So solute and solvent, if they like each other, if their intermolecular forces are good enough, they will try to dissolve. They will try to say hello to each other. And if they don't like each other, they will be separated. No, they will be separated. They will be just like an introvert. They don't talk to others. So if the interactions are good enough, then this will be a solid will easily dissolve in liquid. For example, NaCl. For example, NaCl dissolves nicely in water. Now, temperature effect. You just need to remember, temperature is a parameter which affects the solubility of solid in liquid depending upon its thermodynamics. If the reaction is liberating heat means if the reactants are of high energy but products are of low energy and the heat is dissipated in the environment, in the reservoir, the big one, the surrounding. Now what happens there? You need to reduce the temperature of the reaction vessel further to push the reaction in the forward direction. I am sure you have studied this in chemical equilibrium. So to push the reaction of endothermic processes which require heat, then you need to increase the temperature, solubility will increase. And if the process is exothermic, something upon dissolution in water liberates heat, then you need to decrease the temperature. Is that clear, everybody? For exothermic, you know what? Exo is a word which means out. Exo is a word which means out. So which is throwing energy outside, throwing heat outside, right? So the temperature increasing, then the solubility decreases. Understood? Good job. Now the pressure, since solids are incompressible, there is almost nil effect of pressure on the solubility of solid into liquids. Is the first thing clear, everybody? Is this thing clear, everybody? Sure. Let's move to the next one. Yes, the gas in liquids, the carbonated drinks. So higher will be the intermolecular interactions, more will be the solubility. When we study that, the CO2 dissolves nicely in water, but helium does not. That's the reason, because helium does not have any sort of intermolecular forces to be made with water, hence it is poorly soluble. All right. Then we have something called critical temperature, something called TC, that we study in gaseous state chapter in 11th grade. The TC, as high the TC is, it's easy for us to liquefy that gas, and then mixing will also become nice. Mixing will also become very facile. So higher is the TC, it has to be higher is the TC, higher will be the solubility. Higher is the TC, higher will be the solubility. Please fix it. All right. Now liquid in liquid, volatile liquid or a non-volatile liquid depends upon the nature of the solute and solvent will decide whether they are mixing with each other or not. Here we are going to study something called Raoult's law, and here now we are going to study something called Henry's law. Is this much clear? Now when you are making notes, you need to just proceed from here, because Henry's law is very, very important. Raoult's law, again very important, and I am going to tell you that Henry's law is a special case of Raoult's law. Let's proceed, everybody. What is Henry's law? So if Henry's law was not discovered, we would be it would have been very difficult to make Pepsis. I am not saying it's impossible. So, but the chemistry, the process, the technology of it was a little bit in dilemma. What to do, how to improve the solubility, what the temperature and pressure things are to be done. So, you know, my professor from ISC, my professor, PhD supervisor used to say that making and baking are the same thing. Baking, or in other sense, you can say working in a laboratory and cooking, they are the same thing. Cooking in kitchen and making things in the laboratory, synthesizing, they are the same thing. So what we are going to discuss over here, we make Pepsi, we create that, we try to dissolve CO2. Unless you know what is the property of that gas, unless you know what is the property of that liquid in which you are going to dissolve that gas, the things will not be that clear, the things will not be that transparent. You need to understand that system to get the best out of it. Let's come back to Henry's law. Henry's law says that the solubility of the gas in a liquid at a given temperature is directly proportional to. So pressure is directly proportional to chi, the amount of the substance. Also, according to the definition that I have brought to you, chi will be directly proportional to the pressure of that gas above that liquid surface. Okay. Now, my question to you, everybody, you might have seen these kind of Henry's law equation, but which one out of the two, when I remove the proportionality constant, there is something called KH, Henry's constant. When I remove proportionality constant, there is KH, proportionality constant, Henry's constant. Tell me which one out of the two you think is the right representation of Henry's law. Which one? Number one or number two? The left one or the right one? Which one? Which one is the right representation? Which one? The answer is both. Sir, how? How is that possible? Both. if you are provided the information in the question, depending upon that, you will be deciding which equation to be used. For example, KH, can you say that KH ka unit? What will be the unit of this proportionality constant? From this, it will be pressure divided by chi. And we know chi has no unit, absolutely no unit at all. So what is the unit that you are left with? Here it will be just pressure ka unit, that's ATM. ATM paise wala ATM nahi. This is atmosphere. And here chi has absolutely no unit once again. But since you want to make it unitless quantity by multiplying these two, what do we need to do? So what is the unit of pressure? ATM. So what is the unit of KH that you are going to think? It will be ATM inverse. Do you understand, guys? Both these are correct, but which one to be used? Question will tell you, the statement will tell you. Okay. So depends upon, KH depends upon intermolecular forces between the gas and the liquid. You should know that. And also you should know KH is a property of a liquid. KH is it's a proper same unit. It's a property of that gas. It's a property of that gas, how much things you are going to actually dissolve. Okay. Now KH is Henry's constant, chi is mole fraction of the gas, and now the partial pressure, it depends upon how much of that gas is present. Suppose you have two type of gases present above the surface of liquid. The one which will have higher vapor pressure will have more possibility to undergo dissolution in water. All right. This is the graph that explains Henry's law. Since pressure is equals to KH into chi, since it is equals to the simple straight line equation KH into chi, can you imagine this as y is equals to mx? I can plot x mole fraction on the x-axis and partial pressure or pressure on the y-axis. So this goes from the origin, and that very well verify the mathematical data also, because at that point, which is called an origin, if there is no mole fraction, there will be no pressure of the gas. If there is no pressure, no solubility of the gas also. So what's the slope of this graph, everybody? It's KH, Henry's constant. Remember, Henry's constant. This is a variation of Henry's constant with temperature. You know that we like soft drink when they are cold. Do you like soft drink when it's hot? No, you have to just, you would like to take it out from the refrigerator and then drink it nicely. Suppose I give you a cold, I invite you at my home, and or you invite me at home. Let's do the other way. And you offer me, sir, take this take this soft drink. But it was kept in my kitchen for maybe 5-7 days. It was not in the refrigerator. I may not like it, because as you increase the temperature, outside temperature is much higher than the refrigerator temperature. Agreed? Okay. Now the gas which is present in the bottle is no more in the dissolved form. It is trapped on the space left between. Do you see that the bottle does not have liquid filled up to the brim, up to the cap? So we have to leave some space so that when the gas leaks from, or when the gas comes out from the liquid, gets collected on that empty space given in the bottle. Suppose we do not leave that space at all and fill it up to the top, up to the cap, up to the brim. What will happen? The gas will find no space to escape, because the gas dissolves more at low temperature. This is what I'm trying to tell you. Gas dissolves at lower temperature. But when the temperature is higher, the solubility will reduce and Ks value will also go up. Temperature and KH, they go hand in hand. And if the temperature is high, KH is high. If KH is high, what happens to solubility? Solubility goes down. So KH increases with increase in temperature, but solubility decreases. That is something you need to know. This graph is extremely important. They can check with what is the order of this T1, T2 and T3. As KH is higher, how is KH higher, sir? Check the slope, beta. Slope is this. For this one, the slope, and for third one, as the line goes steeper and steeper and steeper, the slope increases, and this one has the higher slope, hence the T1 value is also the highest. Understood, everybody? Good job. Shall we move to the next topic now? All right. Now we need to know what are the limitation of Henry's law. You know that. So you might be thinking, sir, in chemistry we see there are limitations always. Yes, because chemistry is the youngest subject in science. Out of physics, chemistry and maths, chemistry is the youngest subject. We knew chemistry from very, very, very old age. We knew it. But chemistry was not developed. It was considered as a black box. It was considered as a black magic. Alchemy was the earlier name for chemistry. Of you, I'll tell you something which about atom. When did we know about an atom completely? Completely, even today we don't know about an atom completely, but all the three fundamental particles, electron, protons and neutrons, we figured out, we discovered neutron in 1932. Now you can consider how youngest the subject is. All right, now some other limitations of the Henry's law. The first limitation is the gas and the liquid, they should not react with each other. They should just say hello, hello, hi, hi. That's all. They should not mix with each other. They should not react then. And just after mixing, they should not change their composition. Their chemical integrity should be maintained. Understood? All right. And the pressure should not be that very high. Pressure should not be too high. Pressure should not be too high. Should not be too high. Temperature also should not be too low. When we think that the temperature, reducing the temperature helps in dissolving the gas, and we then try to decrease the temperature a lot. Don't do that. Henry's law will not be applicable. And we also know increasing pressure increases the solubility. Why not increase the pressure too high? No, don't do that. Henry's law will not be applicable anymore. Then the gas should also maintain its integrity. As I said, it should not undergo any sort of association or dissociation. It should remain as it is. It should remain intact. Understood? All right. Then there are some applications. First is the carbonated soft drinks. As I said, they are packed at a high pressure so that the CO2 dissolves in the liquid that is supplied to you. Otherwise, it is just the sugar solution. And who likes sugar solution? No, anoxia, which is a deprivation of, or something, we can say the amount of oxygen in the blood when it reduces, is known as anoxia, is caused at a higher altitude, right? It's called as higher altitude. And Henry's law says that, and as we go in the higher altitude, the pressure reduces and the gas in our blood also starts dissolving less. Solubility decreases. Mixing of O2 with helium and nitrogen. For sea divers, they generally need to take a tank filled with oxygen. It should not be 100% oxygen. It has to be filled with helium. It should be it should be mixed with helium and nitrogen, so that to avoid bends. There is something called bends, which is one problem when they just come out of water, and then sudden release of oxygen can cause bends in the body. All right. Now we have to study what is solution. Now we are quickly moving to Raoult's law. Miscible and immiscible solutions and completely soluble solutions. Immiscible solution means when we take water in hexane, just mere one example, water and hexane, they are not immiscible because this is a polar solvent, this is a non-polar solvent. So they are two anyways not going to talk to each other, they are not going to mix with each other. Make sense, everybody? Right. The partially miscible solution, we can take water and 1-butanol. This is an alcohol. This is also having OH. So OH, some sort of hydrogen bonding may help in associating with each other. Now they are going to be partially miscible with each other. When we have completely miscible solution, we blindly apply, we can then apply Raoult's law. We are going to discuss various varieties of it. Water in ethanol, very famous water in ethanol. Everybody knows water in ethanol. Let's discuss what is vapor pressure. Suppose I take a container and start boiling. Now my question to everybody, you have to answer to me in the chat box, in the comment box. What is the boiling point of water at 0.9 atm? What is the boiling point of water at 0.9 atm? Okay, another question. What is the boiling point of water at 1 atm? Did you think about it anytime? That changing the pressure may change boiling point. Absolutely. The temperature will be varied if the pressure outside is varied. Now, what is pressure basically? The pressure is when you start providing heat to the system, its thermal energy increases, they start boiling. When are they going to start? When the water molecules are going to start boiling. What stage is known as a boiling stage? When the vapors created by that liquid matches with the pressure outside. Matches with the pressure outside. If the container is closed, then outside and inside pressure are different. And when the container is open, outside and inside temperature, they are, outside temperature is how much? 180 m. So the liquid actually has to create pressure equals to 180 m, and that pressure is known as vapor pressure, and the temperature at which vapor pressure becomes equals to the pressure outside is known as boiling point. Am I making sense? When the pressure of that vapors created by the liquid, it becomes equals to the pressure outside, that process, that's temperature, that stage is known as boiling. Understood? Okay. The pressure exerted by the vapors of a liquid when in equilibrium is established between the vapors and the liquid. Suppose this is the container. This is the container, and when I start heating this liquid, there are vapors created. Now these vapors are also going to apply pressure. That pressure will be known as vapor pressure. Okay. The vapor pressure will not depend upon, very important question, very important for your board examination. They ask this question multiple times. Why is vapor pressure, or on what particular factors vapor pressure depend? Vapor pressure does not depend upon the first factor, that is surface area. I can take water in this glass which is of broad bottom, broad surface, or I can take in a very fine, or I can take in a tube, test tube. In all the three, the pressure found will be the same. Okay. It also does not depend upon the shape of the container. As I have taken three different shaped containers, it does not depend upon it. And also the amount of the liquid taken. If I take 1 liter, the vapor pressure will still be the same. If I take 1 ml of water, vapor pressure will still be the same. It does not depend. But on what factors the vapor pressure depend is surface tension. What is surface tension? With what force the molecule on the surface are stretched by, or forced by, or are pulled by the particles below, just below that surface. That is surface tension. The intermolecular forces at the surface tension will directly decide how much will be the pressure, vapor pressure. If the liquid is dense means the particles present just below the top surface are being pulled by the lower particles. So they will not let them go easily. You need to provide more heat, you need to heat it at a higher temperature. Okay. What is the effect of temperature? This is known as 𝐒𝐍𝐆𝐋𝐈𝐒𝐃 equation. This helps us in finding out how the vapor pressure is actually changing with the temperature. So you just need to remember this is ln of P2 divided by P1. What is P1 and P2? These are the temperatures, T1, T2, and these are the vapor pressures, P1 and P2. P2 is the vapor pressure at temperature T2. P1 is the vapor pressure at temperature T1 is equals to delta H. What is this delta H? For vaporization. Since we are heating water from its liquid state to make water gas, what is the energy? Delta H, vaporization, divide by R, the gas constant, 1 by T1 minus 1 by T2. This is the formula. Just remember T1 minus T2, but here the pressure is P2 divided by P1. This is known as 𝐒𝐍𝐵𝐋 equation. Understood, everybody? Shall we move ahead? Great. Let's move to the next part. This is called Raoult's law. Now, what is Raoult's law? Raoult's law says that this system is going to be applicable on liquid phases. Suppose I have one liquid taken in this container and it starts evaporating. If it is a pure liquid A, I am filling it with pure liquid A, then the pressure created by the vapor is denoted by P naught A. What is P naught A? The vapor pressure created by the pure liquid, 100% pure liquid. I take another reaction vessel which contains another liquid of some other nature or similar nature, and that is B. The vapor pressure created here will be P naught B. But now when I take a mixture of A and B, this is A plus B, some amount of A is present, some amount of B is present. Now the pressure here, PA and PB will be valid. They will no longer be P naught A, P naught B. The vapor pressure, PA, is known as partial pressure. Partial pressure PA is now directly proportional to how much of the component is actually present. Do you remember? Similar case we were discussing when we had Henry's law. Remember? So Henry's law said that the partial pressure directly proportional to the solubility is directly proportional to the amount of the substance, and that was equals to KH into chi. But Raoult's law says that the partial pressure is directly proportional to chi once again. This was according to Henry's law, and this is according to Raoult's law. When I replace the proportionality with a proportionality constant, that's P naught A into chi of A into chi of A. When the solution becomes that dilute, when these two are actually the same, when the proportionality constant becomes the same, it becomes Henry's law. So Henry's law is a special case of Raoult's law. Understood? Okay. Now to remove the proportionality constant, as I have brought a constant value P naught A into chi of A. P naught A is a constant value because that's never ever going to change, as we have discussed, right? So vapor pressure does not change even if I take less or more quantity or another vessel or surface area is changed, right? Okay. So it becomes a fixed quantity. So P naught PA will be equals to P naught A chi A, right? PB will be equals to P naught B chi B. Now, according to Dalton's law of partial pressure, the two gases or the two vapors are what? Vapors are basically gases. But there is a very clear distinction between a gas and a vapor. Anything that can be condensed is known as vapor. Like water vapor, we don't say water gas. Anything that can be condensed is known as vapor. Now, according to Dalton's law of partial pressure, we can add the partial pressure to find out the total pressure. We have total pressure equals to now PA plus PB. Now, what is PA? PA is equals to P naught A chi A, and that's equals to P naught B plus P naught B chi B. If you want it in just in the terms of chi of A, we know from this equation chi of A plus chi of B equals to 1. Remember, mole fraction summation is always equals to 1. Now P naught A chi A chi A can be replaced as if it is equals to 1 minus chi B. Also, you can replace chi B in the terms of chi A. Chi B can be written as 1 minus chi A. Did you follow this Raoult's law, everybody? So Raoult's law final expression comes out to be, I'm writing it here, P total is equals to P naught A chi A plus P naught B chi B. This is by the virtue of Dalton's law of partial pressure, which involves this Raoult's law. This thing is known as Raoult's law. This is due to the Raoult's law, this is due to Raoult's law, but this summation is due to Dalton's law. Remember. Okay, let's move further. One more thing here, everybody. If I take this container and collect vapors here, these vapors are also going to have some compositions. This was the liquid having some composition chi A, chi B. This liquid was having composition chi A, chi B. But this vapor will have a composition Ya and Yb. Ya is equals to, that's again due to Raoult's law, is due equals to Pa divided by P total. Understood? This is very important. The vapor fraction, the composition, this is the composition in the vapor phase. Composition in the vapor phase. Composition in vapor phase. Understood? Similarly, you can say Yb will be equals to Pb divided by Pt. This is very, very, very important. One thing you should know, according to Raoult's law, Pa equals to P naught A chi A. Also, Ya equals to Pa divided by Pt. Perfect, everybody. Let's move. Now, I have already brought down the formulas here, which I have just discussed with you, that Pa is equals to Ya into P total. You should know what is Ya. Ya is equals to the composition of component A, composition of component A, component A in vapor phase. In the vapor phase. Good, very good. Now, when we know chi A plus chi B equals to 1, we can replace them in the terms of YA and P naught A also. YA and P naught A also. So this becomes your final expression if asked in terms of composition in the vapor phase. Understood? So YA are the mole fractions or the composition in the vapor phase, YB also. But Chi and Chi B, they are in the liquid phase. Now let's try to plot this graph. When we try to draw this graph, we know that YA, when we know that PA is equals to P naught A into chi of A, this is y is equals to mx with no slope at whatsoever, 0. C is 0. So if I draw, this is something called closed graph. For the very first time you study closed graph in this chapter in chemistry. This I want to draw it as a PA, and I want to draw chi here in the x-axis. So when chi a equals to 0, if you put down the value chi a equals to 0, PA also becomes equals to 0. So obviously we have to start from the origin and go up to here like that without any intercept. This is the same thing drawn over here. Suppose this is at chi b equals to 0 and chi a amount equals to 1. On the same axis, we can plot chi A and chi B both. When chi A is 1, just 100% pure A component, it will be having its highest pressure over here, P naught A. But when you have 100% amount chi A equals to 0 and chi B is equals to 1 here, only component B is present, 100% pure, its total pressure at that situation would be P naught B. This represents total pressure, which was equals to P naught of A into chi of A, P naught of A into chi of A plus P naught B into chi B. Understood, everybody? This is representing a straight line. Again, it's a straight line. This representing the partial pressure. Let me write down here PB equals to P naught B into chi B. This represents PA equals to P naught A into chi A. Understood? All clear, everybody? This is a straight line. This is called a closed graph, a straight line. But this represents the total vapor pressure involving the the composition in the liquid phase. This also straight line, straight line. I have taken a component B considering it is more volatile in nature, hence the vapor pressure is higher than the vapor pressure of A. You can do it otherwise also. You can do it otherwise also. Totally your wish. But you should be in a situation to draw this in the examination, in this graph in the examination. Let's proceed, everybody. So there are two type of, just like we know PV equals to nRT, that equation is valid for ideal gases and not valid for real gases. Similarly, this Raoult's law is applicable for ideal solutions and not for non-ideal solutions. So we need to first understand what are ideal and non-ideal solutions. So something that follows Raoult's law at all the temperatures and the concentration range is known as ideal solution, and that will have its PT exactly equals to the formula that we just derived, no deviations at all. Suppose I have a component A present in the medium and then component B is also present. So A and A, this is not a bond. A and A are interacting with each other. B and B will also interact with each other. But when I mix these two together, A and B will make the interactions. So these are some sort of interactions which are represented. A and A is interacting, B and B is interacting. Now when I add both of them with each other, when I mix with each other, now what happens? A and B, they have to interact with each other. If the interactions are almost the same, there is absolutely no difference. The interaction between AA, original interaction, between BB, original interaction, and between AB, the final one. Now in the mixture, if they are the same, no difference. So the partial pressure will not change. The partial pressure will remain the same. In this system, there will be no change in the enthalpy of mixture, no change in the volume. Suppose you mix 10 ml of A, 10 ml of B. When you mix them, total volume will be exactly 20 ml. Whatever is the type of solution, its entropy will always be positive, and its free energy change will also be negative, will always be negative. So these two things you can note down, they will be always fixed. But what happens to when you discuss non-ideal solutions? In non-ideal solution, there are two kinds. One is called positive and negative deviation. One, in positive deviation, the vapor pressure is found to be higher than the calculated vapor pressure. How is that possible? Suppose there are two friends and they hold their hand so tightly with each other, and there are two people who don't like each other, and they from very far they say hello, hello. So which kind of interaction you think is a better one? The one who is meeting, hello, handshaking with each other, correct? That is a stronger interaction. So if there are two type of components present, A and B in a mixture, and they hold each other tightly, now these two are going to be, they are mixing with each other, and they are this has to be this side. So they are holding each other tightly. What will happen overall? Then the negative deviation will happen. They don't want to lose each other. They don't want to lose their contact with each other. Hence, you need to push more energy. You need to provide more energy so that they evaporate. Understood? I'm explaining once again. Please fix this. When you have two components present and both of them now have better interaction with each other compared to when they were pure in nature. For example, water and ethanol. Water and water molecule, they will have hydrogen bonding. Water and ethanol, they too will have hydrogen bonding, but weaker hydrogen bonding. Then water had hydrogen bonding with itself, or ethanol had hydrogen bonding with itself. So weaker bonding forms between water and ethanol molecule. Hence, evaporation becomes easier. Did you follow that? If evaporation becomes easier at the same temperature, the vapors produced will be more in amount. Hence, such kind of solutions which show a higher vapor pressure than the expected value, than their individual vapor pressures of the pure solvents, that is known as positive deviated non-ideal solution. I'll show you the graphs also. So total pressure will be found out to be greater than the summation of the vapor pressure of component A and component B present respectively. Here the delta H mixing will be greater than 0, and the delta V will also be greater than 0. When you mix 10 ml and 10 ml of two solutions, overall it will be greater than 20. No, it will not be 40, 50, 60. 20.05 or 20.1, 20.2, something like that. Okay. These two things I have already told you, delta S mixing, delta G mixing also. Okay, example, you should know that water and ethanol, very important example. Water and ethanol makes a positive deviation known ideal solution. Water and acetic acid solution mixing, they form negative one. Here the vapor pressure will be lower because the interaction between these two components are now greater, stronger interaction. Hence, they don't want to lose each other. They don't want to get out of their contact. They don't want to do that. They want to still stick. And if you want to lose their contact, you need to provide more energy. More energy means higher temperature. But since we are studying all of these are at a fixed temperature, same temperature, now we know that this will be boiling at a higher temperature and producing less vapor pressure at the constant temperature T. Understood? Okay, good. This is the graph that I was just telling you. These are also given to you in your NCERT. Please have a very careful look over here. Positive variation, positive deviation from the Rolle's law. As we calculated, this was my expected graph, right? This was my expected graph. This is my expected line for PA, PB. PA and PB, the component A and B, they will have their own vapor pressure present in the solution. But when we expect their vapor pressure in the solution, it's no more a straight line. It's a curve now. It's a curve now, and the curve is above this line, which means that this pressure, you take any point, these pressures are basically greater than the pressure of, all these pressure values are greater than the pressure of, let me change the color of the pen so that you know now see the things very clearly. Yeah, so this pressure is the max pressure of component B individual. This pressure is the max pressure of the individual solvent A. But in a mixture, Every time, in every different composition of chi-A and chi-B, the pressure is always, see this, the pressure is higher, 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 higher. Earlier you were expecting the pressure to be on the straight line, but they are more. In every composition range, the pressure is higher. The pressure is higher. Why is this pressure higher now? Because solvent, these two solvent together, water and ethanol, they do not like each other much. They don't like each other much. They will just try to evaporate easier than the water as and ethanol. Understood? Ethanol boils at 82 degrees. Water boils at 100 degrees. But when you mix them together, the system boils at lower than 100 degrees. Understood? Lower than 100 degrees Celsius. Now, here component A is present 100%, right? Here component B is present 100%, and in between both of them are present in their respective values. This is called positive deviation graph. You should be in a situation to be able to draw this graph in examination showing the positive deviation. Understood? Positive deviation. This will be always a curve, which means that it does not follow Raoult's law. Raoult's law is no more applicable. Raoult's law suggested that this should have been a straight line, but due to their new different nature of the mixture, A and B interactions, this is higher vapor pressure observed than the expected value. But if you observed lower vapor pressure, lower vapor pressure, lower vapor pressure, lower vapor pressure, what happens now? Now the vapor pressure is lower due to the stronger interaction between A and B than either AA or BB. A and B has a stronger interaction. You need to provide more energy so that to break them. Understood? All right. Okay, is this positive and negative deviation graph clear, everybody? Let's look at some more things now. There are going to be azeotrophs, although this is not at all a part of your NCRT, but you should be aware of the term what is azeotropic mixture. Azeotropic mixture is the liquid mixture of the two miscible liquid. Remember, it has to be two miscible liquids which distill over without change in the composition. What does it mean? Very technical term here. So suppose I take a 50-50 mixture of the two components, two liquids together. Now I start boiling with this expectation that I can take out one component first and then the second one, fractional distillation. But here such kind of fractional distillation is not possible, because when you heat them, both of them boil at the same time, produce vapor at the same time. Understood? Okay. That is known as azeotropic mixture, which is one kind of non-ideal solution. There is something called maximum boiling azeotrope. A mixture of HCl and H2 forms maximum boiling azeotrope. So that when you mix these two, now the system will boil at a higher temperature than their individual boiling point. No matter what is it. No matter, it will be greater than that. And if it is minimum boiling azeotrope, then for example, mixture of benzene and water, this mixture will boil at a lesser temperature than the individual boiling points. But at that particular composition, not at the entire range, at that particular composition. For example, HNO3 and water, if you mix both of them at 68% and 32%, this mixture boils at 393.5 Kelvin. Do you see that? This temperature is not at all a boiling point of water and HNO3. Okay. It's a non-ideal solution. For your further competition examination, this might be very helpful. Okay. Ethanol mixed with water will boil at 351 Kelvin. What's the boiling point of ethanol? I said it is 82 degrees. 82 degrees, when you convert it into Kelvin, you just need to add 273. How much it will be the total, everybody? This will be 355. Am I right? Right? Okay. So 355 Kelvin, and this is water. Water, we know that it boils at 373 Kelvin. You know, everybody, 100 degrees Celsius, 373 Kelvin. Do you see that this temperature is lower than the boiling point of ethanol? Understood? Boiling point is reduced now of the mixture. This actually the technique that I used to use when I was working in the laboratory every single day for reactions. Suppose you do a reaction and you are left with some moisture in there. Some amount of moisture is left over, or some sort of water contamination has come, and you are not able to heat it at 100 degrees Celsius to remove water. Removal of water is very, very, very difficult. So what we used to do, we just add some amount of ethanol, trying to make azeotropic mixture so that you can boil it at a much lower temperature, almost 20 Kelvin lower temperature. You can now heat it safely and remove water. Understood? Okay, everybody, let's move and just have a quick look at these azeotropic graphs, although they are not necessary to be. So this is the point I was mentioning, which is azeotropic composition. At this stage, the composition of the liquid as well as the composition of vapors will be exactly the same. You will never ever be able to separate them. This becomes your another component where azeotrope has formed. Here, these two compositions in the liquid as well as in the vapor phase, they both will be the same. Be careful, this is temperature into mole fraction, temperature to mole fraction graph. This is also vapor pressure to mole fraction graph. The image is exactly mirror image of it. This is mirror image of it. The vapor, as the pressure increases, we know as the pressure increases, what happens to the vapors? They try to be in the liquid form. So this top region will represent liquid, and when the pressure is less, they will be in the form of vapors. As the temperature increases, what happens to a liquid? It tries to be in the vapor form. As the temperature is less, what happens to it? It tries to remain in the liquid form. These are the two graphs you should look at just for once, so that you should be able to identify that these are the azeotrope graphs. More than that, not required. This is the graph for minimum boiling azeotrope. Do you see that? This is the point at which the vapor pressure is highest, and that's what we wanted to do. We wanted to increase the vapor pressure, So you see that, everybody? The vapor pressure, the mixture at this particular composition is higher than the vapor pressure of this component Y, as well as higher than the vapor pressure of this component X. This is very, very, very useful technique in industry and in academic laboratory to make several organic compounds, or several research is being done. Okay, and here you can see that this is the temperature, which is the lower temperature, then this will be the temperature of the component, one particular component. Let's say this is the boiling point of X, this is the boiling point of Y. This boiling point of the mixture, this boiling point has been reduced. This boiling point is lesser than the boiling point of Y, lesser than the boiling point of X. To do such things, we need to make non-ideal solutions, and non-ideal solutions can make azeotropic solution at one particular composition. For example, HNO3 and water I have just discussed. Okay, everybody. Now, now we are moving to the second part of this talk, which is very simple and straightforward: colligative properties. Colligative properties are those properties which depends upon the number of the particles present, and they are totally independent of the nature of the particle. What is N here? The number of particles present. Number of the particles present. They are not at all dependent upon the nature of the particle. Number of particles, or number of solute particles, to be specific, and independent of the nature of the particle. There are 4 such properties. The first one is called as RLVP. Remember, RLVP, not lowering, not just the lowering in the vapor pressure, or not just the vapor pressure, relative lowering in the vapor pressure. This is lowering in the vapor pressure, delta P. This is with respect to one component, P naught A. A is solvent, that is equals to chi of B, so that when you find out that it comes out to be directly proportional to the number of moles of B present, number of moles of solute present, the particles of B present, number of particles of B present, it becomes a colligative property. Similarly, the second one is elevation in boiling point. It has a tremendous amount of colligative property. They have huge applications. Elevation in boiling point. So in some cold regions, if there are some roads which are blocked by snow, so what we do, we sprinkle salt on that ice, right, on the snow, so that its melting point, its melting point reduces, depression in the freezing point, its freezing point further reduces, melting point further reduces, and then it's easy to clear off the rods. And we can take the ice, we can take the snow away very easily, unless if it starts melting at that temperature, it will be very difficult to clear water from the rods. So elevation in the boiling point, depression in the freezing point, and also osmotic pressure. What is the use of this colligative property at first place is to calculate the molecular mass of the unknown component added to a mixture. I'm repeating, the colligative properties are basically used to find out molecular mass of unknown solvent, or solute. Experimentally we can figure out what's the molecular mass of it. So from this also we can figure out, from here, various techniques. But this osmotic pressure is of immense use because we use it for all the biological or the protein properties, macromolecular properties. Okay, let's discuss all of these one by one. RLVP, relative lowering in the vapor pressure, suggests that there is a relative lowering. This is lowering in the vapor pressure, LVP, with respect to P naught A is equals to chi A. And we know chi A is equals to number of moles of B divided by total number of moles, Na plus Nb. This is valid for the dilute solutions. Also, as we say, it's applicable for dilute solutions. And when we add a non-volatile solute, if we add a non-volatile solute, the Pt, which is equals to P naught A into chi of A plus P naught of B into chi of B. If it is a non-volatile solute, what will happen, guys? This whole term will go to 0 and total pressure will be just equals to P naught of A into chi of A. Now, the delta P value, which is equals to change in the pressure. Initially, the pressure was a P naught. Now, the pressure of the solution is Ps or P total, which is equals to P naught A 1 minus chi A. And that can be written as equals to P naught of A into chi of B. And then delta P divided by P naught of A is equals to chi of B. This is what I have on the top. See here. Understood, everybody? If you have a non-volatile solute, this will be 0. If you have a very dilute solution, then also you can ignore Pb chi B. Okay. This is another relation which is applicable when the solution is very dilute. Number of moles of Nb are so less than number of moles of A, so that you can just ignore this. Or when chi B is less, obviously the same thing in just another words. You can ignore Nb if Nb is very less than Na. Okay, that was your first property. Now let's discuss elevation in the boiling point. Let's read this graph first. Let's try to understand this graph first. When I draw this line, originally there is this particular line which is just for the pure solvent. I'm drawing it once again here. Suppose I draw this line here and I am keeping it equals to 1 atm. Here it is 1 atm. And now I start reading vapor pressure here, and this is the temperature. So I am continuously increasing the temperature here so that the vapor pressure matches to 1 atm. So what is that temperature known as, guys? This temperature will be known as boiling point. But when I add something to that solvent, now I notice that I need to heat more to match it to to the vapor pressure equals to 1 atm. That's new del BP, new boiling point dash. So if earlier boiling point is written as T naught B, the new boiling point is noted as a TB, then the difference between these two is known as delta TB. And delta TB, experimentally, delta TB is found out to be directly proportional to molality. Molality, I'm repeating, molality. And when you remove this proportionality constant, delta TB is equals to Kb into M. What is Kb? Kb is molal elevation constant, or ebullioscopic constant. All right. I want you to write down its unit in the comment boxes. So what will be the unit of Kb that you need to mention? That's equals to delta Tb. Always use the dimension analysis. You will be able to get the values. And Kb formula is actually equals to RTb into M divided by 1000 into delta H vaporization, where Tb is the boiling point of the liquid and M is the mass of the system, molar mass of the system, 1000 into delta H vaporization, since we are evaporating the liquid. Since we are discussing the elevation in the boiling point, boiling process is happening over here. Always see that the new boiling point will be equals to old boiling point plus some x value, new value, since it is elevation. This is extremely important to know that your new boiling point will be higher than the old boiling point. All right. Now you should know that the Kb is something which is a property of the solvent, and it will be totally independent of the substance added into it. So it becomes a solvent property of solvent. Okay, good. Now we have depression in the freezing point. Again, delta Tf. Suppose I draw this kind of line once again here. This is my the temperature versus pressure curve, vapor pressure curve. Now, when you try to see that the liquid range is here, this is the liquid range, this becomes the solid range. At this particular point, it starts freezing. But when it is a solution, I see that the temperature has to be further lowered so that it meets here to become a solid. This is my old temperature. This is old freezing point, and this is a new freezing point. So new freezing point will be always equals to old freezing point minus x. So it will be always a lower number. Understood, everybody? It will be always lower number, freezing point minus x value. Remember this relation. Okay, good. This difference between the two is known as delta Tf, which is experimentally found to be directly proportional to, again, molality. And that proportionality can be removed and put equals to Kf, where Kf will be cryoscopic constant or molal depression constant. M is molality. Remember, M is molality here. M is molality. Right? Okay. Now again, Kf is a property of the solvent. It will be 100% independent of the solute that you are going to add. Okay, this is a formula to find out what will be the Kf unit. Generally, it's not much required. Kf value will be always given to you in the questions. Okay. Now, this last and the most important colligative property is known as osmotic pressure. Pi is equals to CRT, where pi represents the pressure, osmotic pressure. C represents concentration. Concentration can also be written as number of moles divided by volume, and by V molarity. And R is the gas constant. Generally, we use R in the liter ATM. That will be 8.314, or you can use 25 divided by 3. If you are using 25 divided by 3, your answer will be little bit here and there. So you need not to worry. Since you are approximating this value 8.314 to 25 by 3 for easier calculation, your answer will be little bit here and there. You need not worry about that. This will be the graph of pi and the concentration, because pi is directly proportional to the concentration at one fixed temperature, and when pi is equals to C into R and T is constant. So C is constant, T is constant, R is constant, T is constant. R and T is constant. R and T is constant. These two are constant quantities, so y is equals to m into x, can be plotted on a straight line passing from the origin. Understood, everybody? Okay. So there are three kinds of solution. One is known as hypotonic. Hypo means, you know, when two people talk to each other and someone speaks louder, someone gets hype. We say, why are you getting hyper? Have you used this term, or have you heard this term when we say, why are you getting hyper? Hypertension. Hyper means more. When the pressure of two solutions, these are the two solutions kept over here. This will apply one pressure. This will also apply pressure on the semi-permeable membrane, so that liquid from less concentration start traveling towards the solution which has higher concentration, right? So that both of them become of the same concentration. This is the osmotic pressure ka concept. So from one solution, solution number 1 to 2, solvent molecules start traveling and they will pass through this SPM, semi-permeable membrane, so that the concentration on both the compartment becomes the same, right? This is actually known as the concentration noted in terms of hypotonic, isotonic or hypertonic. If the pressure here pi is greater than pi 2, then the solution number 1 will be known as hypertonic solution. Solution number 2 will be known as hypotonic solution. After the transfer of solvent, movement of solvent has happened and both have now become of the same concentration. This is known as the two are now going to known as isotonic solution. Same tone, same solvent, same amount of concentration is present in both the solution. Both of them are having now same osmotic pressure. This is of extreme use, everybody. You should be careful when you study osmotic pressure. Now, finally, we have the formulas ready with us, but there is one issue which is known as Van Hoff factor. Van Hoff factor is of extreme importance. We need to understand that this corrects all the qualitative properties that we know. Because when we use an electrolyte in a solution in the form of a solute, then they may associate, dissociate. Some compounds have a property to undergo association. Some compounds have a property to undergo dissociation. Electrolytes, for example, NaCl, when you are taking in a solvent, it dissociates to produce two ions. So then the number of ions that you have added in the beginning and number of ions which are actually present in the solution now, they both are different. Hence, colligative property, they also are found to be different. What you expect and what you observe during an experiment, they both are different. Molecular mass that you experience during an experiment, molecular mass that you had originally added of the solute, now they are different if they are undergoing association and dissociation. Their colligative property measurement will also be of false readings. So to fix all these, Van Hoff factor is introduced, that is equals to experimental colligative property, which is observed, divided by calculated, which is expected. So on paper, you calculate one property and you do an actual experiment, take a ratio. So normal or theoretical molar mass, remember, theoretical molar mass is here and observed molar mass. In case of molar mass, this ratio is reversed. Don't do the otherwise. Okay. Number of moles after association or dissociation. For example, in case of NaCl, when you add NaCl, then the number of particles present in the solution, they will no longer be just one NaCl, it will be Na plus and Cl minus, there will be two. But when you use urea does not undergo any sort of association or dissociation, then that value will be just one. But sometimes there will be weak electrolytes also present, which will dissociate to some extent. For them, we need to figure out what should be that I value. If they undergo association and if they undergo dissociation, we need to have their two different I values. And for the case of dissociation, I value will be equals to 1 plus n minus 1 into alpha, where alpha is degree of association, dissociation for this particular case. And remember, to verify your answer, I value has to be always greater than 1. Example could be acetic acid in water. Acetic acid in water is supposed to produce two ions, acetate and H+, but it does not 100% dissociates. It produces less of those. And if association is happening, for example, acetic acid, once again, very important, very important, in benzene undergoes association, it undergoes a dimerization. So molecule that you took in the beginning was one, were two, but after association, during a course of reaction, the two acetic acid molecule, they are dimerized, and now the number of molecules, they are half, they're reduced to half. So then for that case, I value will be equals to 1 plus n minus 1 plus 1 by 1 plus 1 by n minus 1 into alpha. Very, very important formulas you need to remember. For every kind of colligative property calculation, I suggest you people to use these corrected values, corrected colligative properties, multiply all of them with I and I, so that you get the right answer. So if the question is mentioning any electrolyte, always look for Ventov factor. If the question mentions that and the solute added undergoes association or dissociation, always check for alpha, always check for I value, and then do the needful calculation. Okay, everybody, that's all. I believe this is all we need to discuss today. So I have brought to you all the summary. For example, we discuss all these concentration terms. We calculate how to find out ppm, molarity, normality, molarity, ppb, ppm. All sort of calculations are done. And also we have, this is a mind map you can create in your head. The solution chapter has types of solvent: gaseous, liquid, solid and liquid. The solubility terms also we discuss in detail. Some sort of gas and gas mixture, liquid gas mixture, gas liquid mixture, solid mixture. All sort of mixtures are possible. Also we discuss how solubility is affected by various parameters: effect of temperature, pressure, temperature. Henry's law we discussed, which is a special case of Raoult's law. Also we figured out colligative properties, which are osmotic pressure, depression in freezing point, elevation in boiling point, relative lowering in vapor pressure. We also find there were positive and the negative deviations of the Raoult's law. Azeotrops also we saw that there were various thermodynamic properties, delta H, delta S, and delta G associated. What are the examples? Yeah, you people must remember few examples of ideal solution and few of non-ideal, positive and the negative. So in the questions, they generally ask to identify or to at least write down the differences between ideal and non-ideal solutions and their few examples. So I recommend you to people to definitely remember a few examples, not many but few. Yes. Okay. So non-ideal solutions, they do not obey Raoult's law, but Raoult's law is obeyed by ideal solutions. That's all, guys, and thank you so much for attending the lecture, and we will meet again soon. This is your teacher, Dr. Lakshya Kathuria. Hope you like the session. Till then, goodbye. See you guys.